who didn't go to my review last time? Raise your hand. What is it? Almost half. Almost half. Okay. Okay. Periodic trend. Okay. We have 4 trends that you need to know how to deal with it. First one from both sides. Last time. One more. Okay, alright. We know both sides of atomic radius. How do you know which one is bigger, which one is smaller? Okay, then we go to ionization energy. The energy that requires to remove 1 electron. Alright? We haven't talked about electron affinity yet, but you see kind of opposite to electron opposite to ionization energy. It's the energy when an atom accepts electron. Okay? Ionization energy is the energy that you use to remove electron. EA, electron affinity, we gain, right, when an atom accepts electron. Yeah, we'll talk about that in detail. And the last one, we talk about electron negativity, EA. Okay? Yeah, we're going to pull the rope a little bit, yeah, you will see. Okay. Just a little bit, just a little touch from last time, size, what about atomic radius. Alright? So we have to know trend down to the group and across the period. Take a look at down to the group. You see electron configuration. Lithium, right? The electrons is added into only 2s. Pretty small. Go to sodium. Electron is added to 3s. It gets bigger. Right? Go to potassium, rubidium, add to 4s, 5s get a lot bigger. So down the group, the trend will be get bigger. Okay? From top to bottom. Bottom, big. Remember that. Okay? At the bottom, it's big. Yeah, because of electron configuration. Now, what about across the period? Okay, let's do across the period. From electron configuration, you can see all the electron is added to only 2s, 2b, not that much different in size. Right? The shell is pretty much the same, but what's the big difference? Across the period, what's the big difference? We add more proton. Right? More proton. You know proton attract electrons. Right? Proton attracts electrons. More proton, what does it mean? More protons. More pull, right? More attraction, so it gets smaller. So you want to see which one is bigger, smaller. Across the period, more proton. We get more proton. Right? So the big one will be less proton. Less proton, weak interaction. Get big. Alright? So we have 2 trends so far. We have down the group, yeah, at the bottom, okay. And we have across the period, less proton, weak interaction. Okay. Alright? Now, how do we deal with the problem about size? We have to compare between, compare atoms, which one's bigger, which one's smaller. First, we take a look at the period. Alright? Bottom, big. Yeah, from electron configuration, but we don't really need to do that. Just find them is if the atom is at the bottom, that's big. Right? Now, after we done the first one, we take at the same period, we take a look at proton. After we done this size, yeah, we have the same period, pretty much the same size. So what makes the difference is the number of proton. Less proton is big. Alright? So let me show you the first one. Don't need to do electron configuration, right? Don't need to do electron configuration. We're gonna find an periodic table and just answer them right away. Alright, take a look here. So if I give you selenium, krypton, oxygen, sulfur, lithium, and beryllium, how do you deal with it? Compare size. Yeah, first one, try to find the group first. Try to find where they are in periodic table. Right there. We have lithium, beryllium, and oxygen in the same period. You see that? Sulfur gets lower. Selenium and krypton in the same period. Alright? So we're going to group them according to period. We have period 2, oxygen, lithium, beryllium. Group 3, sulfur, 4, krypton, and 5, selenium. Who's the biggest? Selenium, down the group, right down the group. At the bottom is big. Selenium is right there. There's something wrong. Krypton should be there. With selenium. All right, 1, 2, 3, 4. Period number 4. All right, period number 4. Check a little bit. Selenium and krypton should be period number 4. All right. Now, let's do it. So we get krypton and selenium in the same period. Okay, we have sulfur, get a little smaller, oxygen, lithium, beryllium in the same period. Right, so krypton and selenium are the biggest one. So how do we deal with it? Next one, the same period, you take a look at proton. Right, take a look at proton. So who has a big one has less proton, less interaction, get big. Okay, who has less proton between krypton and selenium? Selenium is right there, right? Selenium, less proton and krypton, so selenium is bigger. That's all that light size. Okay. And we have oxygen, lithium, beryllium, right? The same period. So we take a look at proton. Okay. Less proton is big. So lithium, 3 protons, beryllium, 4 protons, oxygen, 6 protons. So it's going to be like that. You should get something like that. Selenium, krypton, sulfur, lithium, beryllium, and oxygen. Okay? So when we deal with the problem with size, ask you to find, to compare size, you take a look first. Look at the period, where they are. Okay? At the bottom is big. For an atom at the same period, we look at the number of protons. So less proton, big or small? Big, right? Less proton, less interaction is big. Now, let's try. Write it guys. Yeah, find the periodic table where they are. We have boron, neon, barium, iodine, chlorine, phosphorus, and francium. Which atom is at the very bottom? Very bottom. Which atom? Francium. Francium right there. That's francium. You're going to find, you can really have the table a little bit. Okay? So francium is going to be the biggest one. When we rank size, we talk about period first. Take a look at the period. Okay, at the bottom is big. So first one, try to find them. We have francium, barium, iodine. We have period number 5. Then phosphorus and chlorine, the same period. Boron and neon, the same period. Okay, so I'm going to group them. Period number 2 to 7. All right. So from here, who's the biggest? Tell me again. Yeah, francium is the biggest. All right, the smallest will be either boron or neon. All right. So we done with period. What we take a look next? Proton. Okay, we take a look at proton. Less interaction, big. So the same period, take a look at proton. We have phosphorus and chlorine. Okay, phosphorus has less proton and chlorine, it's bigger. Boron and neon. Boron has less proton. Boron is bigger. So, answer should be francium, barium, iodine, phosphorus, chlorine, boron, and neon. Alright? So, take a look at period first. Yeah, 5 in at the very bottom. Yeah, the same period, we take a look at proton. Alright, so that's the size. Now, ionization energy. Okay, good. I'm going to go a little bit fast here because I called volatile. Right? So ionization energy is the energy needed to remove an outer shell electron from an atom. Right? Like from lithium. Yeah, become lithium ion and loses one electron. Okay? So, just a little bit understanding about ionization. So we have a lithium in a gas phase, right? Neutral lithium. Test it, right? Add energy to it, we call IE1. So we become lithium plus and one electron coming out. If we do one more time, we call this IE number 2. Okay, we do second time. And lithium loses lithium ion, not just neutral lithium. This one's lithium ion. Loses one more electron. Okay, become lithium 2 plus. And loses one more electron. If we do one more time, we call it IE number 3. Okay, and lithium 2 plus loses one electron, become lithium 3 plus. If I ask you, compare between IE1, IE2, and IE3, should this energy be the same amount? Why not? No, for sure. Why not? Good. All right. We have the same proton, right? This proton pull 3 electrons at the beginning. The same amount of proton, right? Have interaction with these 3 electrons. Once it loses 1 electron, so lithium, the same proton, same amount of proton, they have 2 electrons left. So this string is shared between 2 electrons. So first one is shared between 3 electrons. Second one we share between 2 electrons. So the attraction will be stronger or weaker? Stronger, right? The same pull, the same string. 3 electrons and 2 electrons. Share between 3 electrons and share between 2 electrons. So IE2 basically is higher than IE1. We need more energy to remove electrons. Even IE3, the same amount of proton per 1 electron. Alright, so more interaction. So IE3 will be the highest. As before, IE1, IE2, IE3, you should need more energy, more and more energy. Alright? So for that, identify energy required for each step. Okay? First one, from neutral fluorine, I just tell you, neutral fluorine becomes fluorine plus, what do you call that IE? IE1. Alright, we call it IE1. Now, from F plus, right, F plus, become F2 plus. What do we call this energy? IE2, right? And for sure, IE2 higher than IE1 by a large amount. From IE2 plus, from F2 plus to F3 plus, and fluorine loses 1 more electron. So we call that IE3. If I ask you, what is the energy associated with the last one? Be careful, it's okay, be careful. IE1, 2, 3, and 4 combined. Why? How's that? You guys might talk about it. Alright, you guys might ask, should it be IE4? Is it IE4? No. IE4 should be like that, from F3 plus to F4 plus. And F3 plus loses 1 electron. Right? But this one, we have neutral fluorine. And we remove 4 electrons at the same time. Alright, we have neutral fluorine, start with neutral fluorine. We didn't start with fluorine 3 plus, become 4 plus. We start with neutral fluorine, become fluorine 4 plus. And loses 4 electrons at the same time. So we call this IE associated with this. We call this IE associated with this this equation, IE1 plus 2 plus 3 plus 4. We need all of them. Okay, to remove 4 electrons. Yes?
If you're doing them at separate times, is it possible for the IE energy for 2 to be less than it would be for, or more than it would be for 3?
In general, no.
But if it's going to a different subshell, if there's only 1 left, it would be easier to give it away rather than if there's 1 that would go away.
I can't really hear you, sorry. We'll talk about that later. Okay. All right. the trick. Take a look at the trick. Okay? So what we know, what is size so far. Okay? At the bottom, it gets bigger. Across the period, it gets smaller. Now, if I compare between the first one, lithium, sodium, potassium, and rubidium, which one needs more energy to remove an electron? We have lithium, sodium, potassium, rubidium. The group one is group one, or group one. Lithium, sodium, potassium, rubidium. Right? Which one needs more energy, let's guess, to remove an electron? Why lithium is closer to proton, right? Closer to nucleus. As the size gets larger, the outer shell electron, as the size gets larger, the outer shell electron is far from nucleus, right? It's far from nucleus. So less interaction. So we need just more energy to remove an electron. But compared to lithium, the outer shell electron is very close to the nucleus. There's strong interaction. So we need more energy to remove that electron. Okay? So for periodic table, we want to find the highest IE, we go to the top. Right, because of the size. Okay? Now, what about the period? Across the period. Size pretty much the same, right? Pretty much the same. Not that different. I try to make it exaggerate a little bit, make it different. But the size pretty much the same. So what is the difference? Compare between lithium and neon. Which one should need more energy to remove an electron? Lithium or neon? Why neon? More proton. Okay? Across the period, we increase amount of protons. 3, 4, 5, 6, 7, all the way to 10. Neon has 10 protons. More electrons, more protons, more interaction. So you need more energy to remove that electron. Okay? So we have two trends. Okay? We go down group. At the top, is small, so we need more energy. So if you go across the period, more proton, higher ionization energy is needed. Are we okay with that? All right. Have you seen a graph like that? Yeah, like a lining graph. Yeah, it's kind of weird trend, right? Be careful. We can use this trend to like in general, but be careful. Only group 2. And group 3, and group 5, and group 6. Right? Group 2, group 3, group 5, group 6. As we know that group number 3 have more proton, so it's supposed to need more energy. Ionization energy should be bigger. Right? And the same thing, similarly, group 6 and group 5. Group 6 has more proton. Right? Group 6 has more proton, so it's supposed to need more energy to remove an electron, but it reversed a little bit. The reason why it reversed, is, have you heard about half field and full field? Yeah, I'm not talking about that today, okay? Half field and full field electron configuration, go in the text. But be careful when you do the trade. Group 2, more than group 3. Group 5, higher than group 6. Right, everything's the same, but group 2, 3, and 5, and 6, be careful with 4 groups. Alright? Alright, dealing with the problem about ionization energy. So we have two steps. First, take a look at the size first. Alright, at the size. Smaller, higher or lower IE. Higher IE is small, right? More interaction, so higher ionization energy. In the same size, right? Same size, in the same period. We take a look at proton. More proton, we need more energy or less energy? More energy, right? We take a look at the more protons one. More protons, more interaction, higher ionization energy. And number 3, we watch out for 2 and 3, 5 and 6. Yeah, we get 3, 4, and 6 will text. Yeah, for a reason. Okay? Alright, if we give you sulfur, iodine, beryllium, boron, strontium, and lithium, how do you recognize ionization energy?